Okay, so these are the sort of things that we're going to be looking at in section 4.2. We started this a little bit the other day. Go over some more. All right, the first thing we had for answering number 1 and number 2, we had some formulas that we need to remember. We had the sum from I equals 1 to n of c. So how do I take a number c and add c plus c plus c plus c plus c n times? What do you get when you take c plus c plus c plus c? C times n. You add a number up n times. That's the definition of c times n. Sum from I equals 1 to n of I. So this was like 1 plus 2 plus 3 plus 4 plus 5. Keep going. We had a formula for that. What was the formula for 1 plus 2 plus 3 plus 4? N times n plus 1 over 2. That was the Gauss formula. Then we had a sum for I equals 1 to n of I squared. So now you'd be doing 1 plus 4 plus 9 plus 16 plus 25. The formula for that was n times n plus 1 times 2n plus 1 over 6. And then finally the last formula we had was a sum from I equals 1 to n of I cubed. That one was n squared times n plus 1 squared over 4. Here's some good news. What's some good news? What's that? Well, that's pretty much all you need to know for this section. That's true. But there's better news than that. You do not have to memorize these formulas. And when it comes time to take your test, I will give you these. What's that? On a quiz. If you need these formulas on a quiz, I would give them to you. You do not need to memorize these. Okay? You can memorize them if you want. It's up to you. All right, so let's go back to part A here. It wants us to take the sum from I equals 1 to 60 of 4i minus 5. Well, what you can do, I wouldn't expect you to write this all out, but here's the technical things that you do. This is 4 times the sum from I equals 1 to 60 of I minus the sum from I equals 1 to 60 of 5. And my question is, why can I do those things? Why can I split this on the minus sign? Because we're talking about addition and subtraction. As long as I'm adding stuff up, these are summations, as long as I'm adding stuff up, does it matter what order I add them in? Yeah, no. 60 on top of both of them, yep. And then how come I can take this 4 and put it out front? It's really just a distributive property, because think about it. If the 4 is in there, that means you're going to do 4 times 1, plus 4 times 2, plus 4 times 3, plus 4 times 4. You can just factor the 4 out. Okay? So now we use our formula. This is going to be 4 times. What's the sum from I equals 1 to 60 of I? Well, I use this formula over here. The sum from I equals 1 to 60 of I is 60 times 61 over 2. Minus, what's the sum from I equals 1 to 60 of 5? I take 5 plus 5 plus 5 plus 5, 60 times. That's going to be 5 times 60. So now I would grab my calculator. 4 times 60 times 61 divided by 2 minus 5 times 60. My calculator says the answer is 7,020. Questions on that one? All right, part B. Now here's what I would expect you to do. I would not really expect you to split the sum up like I did on this problem. You can if you want to. All I would really expect you to do is say, this is 2 times, how do I take the sum from I equals 1 to 25 of I squared? 25 times 26 times 51. So it's going to be 25 times 26 times 51, all divided by 6, plus 3 times the sum from I equals 1 to 25 of I. I go back to this formula again. 25 times 26 divided by 2. I grab my calculator. 2 times 25 times 26 times 51 divided by 2 plus 3 divided by 6. Thank you. Plus 3 times 25 times 26 divided by 2. I get that number. 12,025. Questions on that one? Number 2. Rewrite the expressions that's supposed to be without the summation notation. Without the summation notation. So notice the difference on these. The difference is I have the sum from I equals 1 to n. I did not give you a specific number there. So what do? Leave n blank? No, you don't leave n blank. Just put n in for n. That's correct. Okay, so what's going to happen? Notice we also have this division by n squared. What do we do with that? Well, I could move it up to the top. If I move it up to the top, it's going to go up to the top. It's going to have a negative exponent. I'm not going to do that. That's not wrong. You just leave it. Okay? So we could do this if we wanted to. N is just a number. We don't know what number it is, but it's just a number. So if I really wanted to, I could take this 1 over n squared, and I could just bring it out front. Just like we did up on problem A, we said 4 is just a number. I can take that 4 and bring it out to the front. 1 over n squared, in this case, is just a number. I can just write it out to the front and get it out of the way. There's no i's in that piece. If it had an I in it, I could not bring it out front. How come I could not bring it out front if it had an I in it? Because I'd have to use my formula for the sum from I equals 1 to whatever. All right, so we're going to have 1 over n squared times. What do I write instead of writing 6i? 6 times n plus 1 divided by 2. Plus, what do I write instead of writing the sum of 3? Cn, where c is the number 3. So that's just going to be 3n. There it is. There it is written without the summation notation. Questions on that one? It says with, but notice I wrote out there. It's supposed to be without. That was a little typo on my part. All right, how about the next one? Same idea, right? Oh, you want to simplify? Okay. I didn't see any directions that said you had to. Do you want to? No. If I were going to simplify, I wouldn't do much. Probably the only thing I would do is I would say 6 divided by 2 is 3. That's probably the only simplification I would do. Unless the directions were very specific and said you have to simplify it a lot. All right, B. Same idea. I'm going to write that 1 over n to the 4th. I'm going to write that out front. I don't need it really. And then I'm going to have the sum from I equals 1 to n of I cubed plus 7i. So I'm going to have that 1 over n to the 4th. And then I write my formula. What's the sum of I cubed? N squared, n plus 1 squared over 4. Plus, what's the formula for 7i? 7 times n plus 1 over 2. All right, so now we're getting very, very close to what we need. Remember the other day we were talking about finding area, and we were talking about building rectangles, and the way to get a better answer was to build more and more rectangles, and then how many rectangles did we want to build altogether? 1,000, or even more than 1,000 would be an infinite number. An infinite number. Problem 3. This is the notation we're going to use for building an infinite number of rectangles. So this right here is the sort of notation we're going to use in a few minutes for finding area under a curve. So we'll have the sum from I equals 1 to n, but then we will take the limit as n goes to infinity. Oh, we haven't done limits in a long, long time, have we? I bet you missed those, didn't you? What's that?
You said you never had using them.
Oh, I lied to you. Oh, rats, I didn't mean to lie to you. But every now and then that happens. All right, so how am I going to find the limit as n goes to infinity of the sum from I equals 1 to n of 6i plus 3 over n squared? Use formula. Which formula? Okay, very good. So you might notice that the summation in 3a is exactly the same summation we did in 2a. So this really just becomes the limit as n goes to infinity. We ended up with our answer 1 over n squared times, I'm going to write this as 3n times n plus 1 plus 3n. The answer is 0? No, I don't think the answer is 0.
Well, wouldn't it be? Why wouldn't it be?
Because I think the answer is 3.
But what multiply everything by 0?
Why would I multiply everything by 0?
Because 1 over n squared, which is 0.
But the top and bottom have the largest power on squared.
The top and bottom have the same power, don't they? Look at what you have on top. I'm going to rewrite this as the leading coefficients. This becomes a limit as n goes to infinity. I'm going to write this as 3n squared plus 3n plus 3n all over n squared. So notice what happens. The power on top and the power on bottom turn out to be exactly the same. So what happens when n goes to infinity and the power on top and the power on bottom are exactly the same? It's the ratio of the leading coefficients, which in this case is 3. So we just found the area under the curve of some function. The problem is I didn't tell you what the function was. And I also didn't tell you what A was and what B was. I didn't tell you where to start and where to end. Who cares?
Wasn't A something, 3 something squared?
No, I don't think so.
Because you have no idea what the units are.
I have no idea what the units were. But we'll get to it in just a minute. In just a minute, we'll start with functions, and we'll actually find the exact area. And you'll see how this works, and you'll see how these sort of things are going to come up. Okay, so part B is very similar. We're going to have the limit as n goes to infinity. We ended up with this mess, didn't we? So I'm just going to rewrite this a little bit. All I'm going to do is I'm going to take this 1 over n to the 4th, and I'm going to distribute it through. So that's going to be n squared times n plus 1 squared over 4n to the 4th plus 7n times n plus 1 over 2n to the 4th. So I used my answer from 2b. I just took the 1 over n to the 4th and distributed it through. So now, what's that limit? No, I don't have to get common denominators. I can handle each one separately. So I look at the first one, I notice the power on bottom is a 4. And the power on top is a 4. If you were to FOIL that all out, you would have n to the 4th, wouldn't you? So the power on top and the power on bottom are the same. So the limit for this fraction is going to be 1/4, because our leading coefficient on top would be a 1, on bottom it's a 4. So that's a quarter. How about this one? This one's going to be 0. How come? Power on bottom is a 4. The power on top is only a 2. The power on bottom is bigger. When your variable is going to infinity and the power on bottom is bigger, your answer is always 0. So this is 1/4 plus 0. Our answer would be 1/4. Questions on that?
The
FOIL them all out or anything?
Absolutely not.
All right.
No, I don't want you to FOIL them all out. What I want you to do is look at them and recognize that this is going to be power 4.
All right.
And recognize your answer's got to be 1/4. Even this one, even though it's not very hard to multiply, I don't really want you to write 7n squared plus 7n. I'm not going to mark it wrong if you do, but I think you're wasting your time. I think you should be able to look at this and say, that's going to be power 2 on top, that's going to be power 4 on bottom, it's 0. Okay? Number 4. Consider the function f of x equals 25 minus x squared. I'm going to skip to b. I'm going to do b first. And I have a reason for doing b first. So why didn't I put it first? I don't know. I wasn't planning ahead. Approximate the area on 0, 5 using n equals 5 and the right-hand rule. Okay, so the first thing we need to do is we're going to start at 0. I like to draw myself a little number line here. And I'm going to end at 5. And it told me n equals 5, which means I'm going to build 5 rectangles. If I'm going to build 5 rectangles, how wide does each rectangle need to be? 1. And we called that, we had a symbol for that, we called that delta x. Delta x is b minus a over n. So in this case, that's 5 minus 0 over 5, which is 1. So I just get to go by ones. That's nice. I really like it when I go by ones. 1, 2, 3, 4, 5. Okay, so using the right-hand rule, my area is going to be, how do I find the height of the first rectangle? Close. Plug 1 into the function. Why 1, not 0? Because we're using the right-hand rule. So our first rectangle goes between 0 and 1. If I'm using the right-hand rule, I'm going to plug in 1. So I'm going to take 1 and plug it into my function. What do I get when I plug 1 into my function? 24. Okay, but I'm going to write it as 25 minus 1 squared, and you'll see why in a minute. That is 24, times the width. How wide is the first rectangle? 1. How wide are all the rectangles? 1. Times 1. Plus, what do I plug into my second? How do I find the height of my second rectangle? I plug in 2 because that's on the right-hand side, correct? So that's going to be 25 minus 2 squared times 1. And I would hope already you happen to see a pattern. What number do I plug in for my third rectangle? 3. So that's going to be plus 25 minus 3 squared times 1. Plus 25 minus 4 squared times 1. Plus 25 minus 5 squared times 1. Now, what I want you to do, I want you to write that as a summation. How would you write that as a summation? The sum from I equals 1 to 5 of what? Of what?
I squared.
I squared. Close, not I squared. 25 minus I squared. Because the first one had 25 minus 1 squared. The second one had 25 minus 2 squared. The third one, 25 minus 3 squared. So this would be 25 minus I squared. That would be the height of each individual rectangle. Times 1, because 1 is the width. Okay? So now, I would have two choices. My two choices would be, I could grab my calculator and I could type up these 5 things and get my answer. That would be okay. That wouldn't be too hard. Or I could use my summation rules and then use my calculator at the end. So let's do it with the summation rules. So what do you get when I take the sum from I equals 1 to 5 of 25? I take 25 plus 25 plus 25. I get 25 times 5, which is 125. Minus What do I get when I take the sum from I equals 1 to 5 of I squared? 5 times 6 times... Nope. This n squared formula goes n, which is 5, n plus 1, which is 6, 2n plus 1, which is 11, all divided by 6. So my final answer would be 25 times 5 minus 55, because the 6 is reduced. Calculator says 70. Is that an approximation?
Yes.
Yes, it is. That is absolutely an approximation. Why is it an approximation? Because we're still using rectangles to find the area, and this is a curve, so are our rectangles going to match up perfectly with the curve? No. It's going to be too big because we're using right hand? Sometimes the right hand is too big, sometimes the right hand is too small. Depends on the graph. This graph, if you were to draw it, 25 minus x squared, is a parabola coming down, like so. So if I pick a spot, like so, and I build my right hand rectangle, my right hand rectangle is going to be too small. So if your function is decreasing, the right hand rectangles will be too small. If your function is increasing, the right-hand rectangles will be too big. You don't really need to know that. All you really needed to know was that your estimation was 70. All right, now we're going to skip to D. Again, I have a reason. I just didn't think ahead. I should have done it this way. Approximate the area on 0 to 5 using n equals 10 in the right-hand rule. All right, so how does things change if n equals 10? The width is going to be a half. So delta x this time will be b minus a over n. That's going to be 5 minus 0 over 10, which is a half. Okay. So we're going to start at 0. We're going to go to 5. But this time we have to go by halves. 1, 2, 3, 4, 5. We'll go by halves. I didn't mark the halves down. Okay, so our answer would be our area is approximately, okay, how would I find the height of the first rectangle? What number would I plug in? 1/2. Why do I plug in 1/2? Because on the first rectangle goes from 0 to half. The number on the right is a half. So that's going to be 25 minus 1/2 squared. And what's the height of that first rectangle? I'm sorry, what's the width of that first rectangle? 1/2. What's the width of every rectangle? 1/2. Plus, what number do I plug into the second rectangle? 1. But I'm going to write 1 as in a funny way. I'm going to write 1 as 1/2 times 2. Very good. So this is going to be 25 minus 1/2 times 2 squared times a half. What number do I plug in for my third rectangle? I plugged in 1/2, then I plugged in 1. The next number is how much? 1.5, which I'm going to write as 1/2 times 3. So this is going to be 25 minus 1/2 times 3 squared times a half. Plus, we'll do one more of these, and then I think we'll convince ourselves we have a pattern. What's the next number that I plug in? 1/2 times 4, right? So I went 1/2 times 1, 1/2 times 2, 1/2 times 3. The next one's going to be 1/2 times 4. So it's going to be 25 minus 1/2 times 4, because that's the number 2, squared, all times a half, plus, and then what would the last one be? 25 minus what? Now the last number you want to plug in is 10, not 10, but 10 times a half. Because the last number we're going to plug in is right here. And that's going to be 5, right? And how do we get to 5? We go 1/2 10 times. So that's going to be 1/2 times 10 squared all times a half. So now, again, I have a choice. I could grab my calculator and I could type this up, and I'd have to type in 10 things. It'd be kind of a pain in the neck. Or, I think, I could write it as a summation. So I'm going to have the sum from I equals 1 to 10 of 25 minus 1/2 I squared. Perfect. Why 1/2 I squared? And then, absolutely, the whole thing still needs to be multiplied by a half. So why is this? This is the height of each rectangle, and this number right here is the width. So why is this the height? Well, because what number did we plug in? For our first rectangle, what number did we plug in? A half. For our second rectangle, what number did we plug in? 2 times a half, which was 1. For our third rectangle, we needed 3 times a half. For our fourth rectangle, 4 times a half. So on and so forth. That's because I increments in an interval of 1. And this 1/2 was something very important in this problem. What was 1/2? It was the delta x. It was the width of each rectangle. All right. So notice we really had the same formula back up here. 25 minus, here we only had I squared. How come we only had I squared? Where here we have 1/2 I squared. What's the difference? Delta x was 1 right there. What if delta x were 1 over 100? Then you would have 1 over 100 times I for each rectangle. All right, so I think this is a lot easier to figure out using our summation formulas than it would be to type each one of these in and have to do all the number crunching on our calculator. So we have 25 times 10 minus 1/4. Where'd the 1/4 come from? I squared I. I squared a half. A half squared is a quarter. And then I'm going to have my formula for I squared. My formula for I squared is n, which is 10, n plus 1, which is 11, 2n plus 1, which is 21, all divided by 6. And then I need to still take that whole thing and multiply it by this 1/2, multiply it by the width of my rectangle. Okay, so that's going to be, I grab my calculator, 25 times 10 minus 1/4 times 10 times 11 times 21 divided by 6. Take that whole answer and multiply it by a half. I get 76.875.
Would it be a half or would it be 5?
Would what be a half?
The 1/2.
1/2 would be a 1/2.
It would be 1/2.
1/2, that's
you
the...
wouldn't use a rule on that?
No. No. Victor.
I'm a little confused on how you multiply
Because the summation formula right here says, I'm going to take 25 plus 25 plus 25 plus 25. I'm going to do that 10 times. If I take 25 and add it together 10 times, that's a fancy way of saying 25 times 10. Yes?
Why is the original function look pretty much the same as the summation?
Ah, very good. Why does the original function look pretty much like the summation? Notice the original function was 25 minus x squared. And in our summation, we have 25 minus, that's no longer x, but it's something squared. It looks pretty much the same. I agree. Why is that? Because what does this part of this formula give? It gives us the height. So whatever this function is at the beginning is going to be used here all the time to find the height.
So in that case, we can simplify this long-standing function formula even further to say it's the original function, but you put in the delta x times I into the original function and multiply the whole thing times delta x.
I was hoping somebody would recognize that. Excellent. So, if I give you a function, given a function f of x, you just figured out the formula for how to approximate the area. The area using the right hand rule is the sum, oh boy, that's an ugly looking summation symbol. The sum I equals 1 to n. What did you just say it was?
The original function.
The original function.
And you put in the delta x times I, and then you multiply that times delta x.
That's absolutely correct. And notice that's exactly what we did on those two problems. On one problem, the delta x was a half. So we had a half I show up in our function, and we had a 1/2 out here. In the other function, in the other example, our delta x was 1, so we had a 1 here, and we had a 1 there. We just had I. That's exactly correct. And we'll see in a minute that because of this piece right here, this gives the height of each rectangle, and this gives the width. We will see in just a minute here that there's an advantage to using the right-hand rule. And the advantage comes in this part right here. If you use the left-hand rule, this part's a little bit uglier. Okay, so let's see if we can figure out what that is. Then, now we'll go back and we'll do part A. And we'll do part B. On the test, you will have a choice of using the left or the right. If you're clever, you're going to use the left because you want to work harder and impress the teacher with your superior algebra skills and make mistakes. And, yeah, not a great idea. All right, so let's look and see what happens if we use the left-hand rule. We're going from 0 to 5, and n is 5 still. So delta x is still 1. So delta x is still going to be b minus a over n, which is still going to be 1. So on our number line, we're going to start at 0, we're going to end at 5, and we're going to go by 1s. Which is nice. I like going by 1s. All right, so our area would approximately be, this time if I'm using the left-hand end of each interval, what number do I plug in the first time? 0. So I would have 25 minus 0 squared times 1. Plus, what number do I plug in for the second rectangle? 1. So 25 minus 1 squared times 1. And I think we see a pattern already. The next one's going to be 25 minus 2 squared times 1. And the fourth one would be 25 minus 3 squared times 1. And the last one would be 25 minus 4 squared times 1. And now here's where this gets a little bit uglier. If I want to write that as a sum, the reason this gets uglier is our summations always have to start at the number 1 in order to use our formulas. So if our summation starts at the number 1,
Can we just say 25 plus the summation of that?
nope. You're going to have I minus 1, aren't you? Because for rectangle number 1, we plug in 0. For rectangle number 2, we plug in 1. For rectangle number 3, we plug in 2. So we're not going to have f at delta xi. We're going to have f at I minus 1. So this would be 25 minus I minus 1 squared times 1. And that makes it slightly harder. Why does that make it slightly harder? Because before you can use the summation formula, you've got to FOIL that. And that's kind of a pain in the neck, isn't it? So we would have to write this as the sum from I equals 1 to 5 of 25 minus I squared minus 2I plus 1, and all that needs to be in parentheses. And we could simplify a little bit. Didn't leave myself much room here. Sum from I equals 1 to 5 of 24 minus I squared plus 2I. So you see what happens when you use the left-hand rule? Because you have to use that I minus 1, you're going to have to FOIL, and you're going to end up with more pieces. Kind of a pain in the neck, right? So why use it? Great question. I don't. I always use the right-hand rule.
Okay, better question, why teach it?
Why teach it?
Because the right-hand rule does the same thing. You could just say there's an S-tier counterpart that has become outdated and we don't have to use.
The reason we teach it is a couple sections down the road, we're going to teach the trapezoidal rule. And when you use the trapezoidal rule, you actually have to use the left side and the right side. So you have to use both of them. The trapezoidal rule sounds scary. It's really not. Instead of building little rectangles, we're going to build little trapezoids. And the advantage of little trapezoids is there's a lot less error. Because if your graph is curving and up on top you have a line connecting the curve, it's much more accurate, much less error.
Is there a triangle rule?
There's not a triangle rule. There's the left-hand rule, the right-hand rule. You can actually talk about the midpoint rule. If you read your book, they'll show you how you can do this using the midpoint each time, which is better than the left or the right. And then there'll be the trapezoid rule, and then there'll be something called Simpson's rule. Simpson's rule is really fun. It looks like a trapezoid, except instead of putting a line on top, we put a little piece of a parabola. And it makes it even more accurate. Simpson's rule, yeah, not named after Homer, named after a different Simpson. Anyway, I'm going to stop with this one here. We could do it, right? I mean, we could figure out that summation. We could use our summation rules, figure it out, get an answer now. Not so bad. But in general, if I wanted to do the left-hand rule,
Just do that same thing, so you can say I minus 1.
correct. For the left-hand rule, you'd have the sum from I equals 1 to n, f of delta x times I minus 1 times delta x. And that's how you would find your height. And like I say, that's slightly uglier because now for every problem you're going to have an I minus 1 to a power. It's not so bad if it's a square, but what if your power is a cube and you got to take I minus 1 and cube it out? How much fun is that? Oh, it's a lot of fun, I agree. Makes it harder. All right, so now we are ready to do what we need to do. And I didn't leave enough room, so I'm going to use the back.
So we're going to apply the link to that formula to get the as x plus
Correct. So, now we're going to take f of x equals 25 minus x squared on the interval 0 to 5, and we're going to find the exact area. And here's how you find the exact area. The exact area is the limit as n goes to infinity, the sum from I equals 1 to n, and now you have a choice. Do you want to use the right rule or the left rule?
Right.
Right rule. That's the right answer. F of delta x I delta x. All right. So first thing we need to do is we need to find delta x. What's delta x? B minus a over n. So in this case, it's 5 minus 0 over n. It's just 5 over n. Where we're gonna build n rectangles, and we're gonna let n get bigger and bigger and bigger and bigger until it's so big we don't know how big it is. We'll let n go into infinity. So in this case, we don't have a specific number of rectangles. We don't have 10. We have n. We're going to build n, and then we're just going to let n get really, really big. All right. So what would this symbol then mean? What would f of delta xi equal?
You take 25 minus, and then you put in 5 over n times I, and then you square that.
Correct. So that symbol right there, that symbol represents the height of each individual rectangle. And what's this 5 over n represent? Delta x, which is the blank of each rectangle. Width. So this symbol is the height of each rectangle. This symbol is the width of each rectangle. So our answer now, we're going to have the limit as n goes to infinity of the sum from I equals 1 to n of the height is 25 minus 5i over n, quantity squared, times the width, which is 5 over n. We do a little algebra. This is the limit as n goes to infinity of the sum from I equals 1 to n. 25, I'm going to write this as minus 25 over n squared times I squared. Why did I write it that way? Well, first off, you agree that those are equal, right? So why did I write the 25 over n squared kind of out front and left the I squared there alone?
Because now we can just put in what I squared.
Correct. What I really need, I'm doing my summation using the i's. So I really need just to sum up the I squared. So what's going to happen with this 25 over n squared? It's really just a number as far as I is concerned. There's no I in that piece. This is a constant. All right, so we're almost done. The limit as n goes to infinity. I'm going to take 25. I'm going to go 25 plus 25 plus 25 plus 25 n times. Plus 25 plus 25 plus 25 n times. 25n. Minus, I have the 25 over n squared. And then I use my formula for the I squared. My formula for the I squared has n times n plus 1 times 2n plus 1 all over 6. And then I got a parenthesis around that whole thing. I still have the 5 over n. Nope, I still don't need a common denominator. What I'm going to do is I'm going to distribute. What happens when I take 25n and I multiply by 5 over n? I get 125n over n. But those have the same power on top and power on bottom, don't they? There's an n on top and an n on bottom. So the limit is 125. Minus. Now look at this one. On this one, if you were to FOIL this all out, you're not going to do it. If you were to FOIL this all out, what would the leading term be? 2n cubed times 25. Right? So the leading term would be 50n cubed. What do you have on bottom? 6n squared. But then you've got another n over here, don't you? So what's the power on bottom if you take this 5 over n and multiply it through? So you'd have 6n cubed on bottom. Here you'd have 25 times 2 times 5 n cubed on top. The power on top and the power on bottom are exactly the same. So it's just your leading coefficients. So it's going to be 25 times 2 times 5 over 6. So absolutely I do not want you to FOIL all those things out. I want you to look at them and realize I'm going to have power 3 on top when I distribute all this out, and I'm going to have power 3 on bottom. And so the only thing that survives is the leading coefficients. That's 125 minus 25 times 2 times 5 divided by 6. The exact area is 83.3 bar square units, whatever our units are. Square inches, square meters, square whatever units we're using on our graph. Questions on that? All right, so in a very similar way, let's do number 5. So we want to find the exact area. So my first question would be, if I'm finding the exact area, what's delta x? How wide is each rectangle? 1 over n, because it would be b minus a over n. That's 1 minus 0 over n. That's 1 over n. How tall is each rectangle? Well, each rectangle is f of delta xi. So that's going to be 2 times I over n minus I over n cubed. Said cubed and wrote squared. I don't know why. Cubed. All I did is I took delta x was 1 over n times I, that's I over n, plugged it into my function. So my area is the limit as n goes to infinity of 2 over ni minus 1 over n cubed I cubed times 1 over n. Ooh, that's not right. What did I forget? My summation symbol. Summation. I equals 1 to n. Sneak that in there. Okay, so notice, again, I just did a little simplifying as I did this. I separated out the i's, basically, because when I do my summation formula, I really need to know what the i's are. The other things are all just constants. They're going to stay there. I use my summation formulas. I'm going to have 2 over n. I use my summation formula for I. Oops, I got a limit n goes to infinity. I haven't done that yet. Limit n goes to infinity. 2 over n. My summation formula for the i's is n times n plus 1 over 2. Minus 1 over n cubed. My summation formula for the n cubes is n squared, n plus 1 squared over 4, and then this whole thing gets multiplied by 1 over n. Once again, I'm not going to do a whole bunch of foiling. I'm just going to check my powers. For the first fraction, what power would I have on top? And in fact, I'm even going to throw the coefficient in there. I would have 2n squared, wouldn't I? And what am I going to have on bottom? 2n squared, because there's that n way over there. And it's helpful that this time this is a 1 over here. Don't have to worry about that little number. So I've got 2n squared over 2n squared. That limit's going to be 1. Minus. What do I have for powers here? N to the 4th, because I got an n squared, I got another n squared. That's going to be n to the 4th. And on bottom I have 4 n to the 4th. On top I have 1 n to the 4th. On bottom I have 4 n to the 4th. So the limit's going to be 1/4. The answer is 3/4. The exact area under that graph is 3/4. If you get a negative number, no, not necessarily. And what I mean by that is, if the original function looked like this, then we would consider that to have negative area because it's below the axis. But we haven't done anything like that. So I will say in this section, if you get negative area, you've done it wrong. All the problems are designed so that you will get a positive area. But in the very near future, we will talk about, when graphs are below the axis, we will talk about having negative area.
What if you have a graph and you're trying to find a place that is below anywhere?
Then it would depend on the graph. For example, if you had a picture that looked like this, then this part would be negative, this part would be positive, but since this part is bigger, overall you would get a positive answer.
But the answer would be the combined area.
The answer would be the combined area of the two. Correct.
So you would actually consider that less area. It would consider it less area than is actually shown.
Correct.
Because
Right. So you would have this portion, which would be a negative area, that portion, which is a positive area. Altogether, you would get a positive number, but it wouldn't actually represent the total area, would it? No. If you wanted the total area, you would do the absolute value, and then you would make this part look like that, and then it would be positive. This one would be the same because it would still be positive. All right, we don't have time for this today. We'll deal with this tomorrow. Notice that up to this point, all of our problems, we always started at 0. Starting at 0 is very nice. It's not so great if you don't start at 0. And we'll take a look at that tomorrow and see what happens when you start at 1. Makes it a little bit harder. See you tomorrow.